Hi there! I hope that you're all doing very well and are excited about today's class. I know I am. I am your personal physics and math tutor, Dr. Rima McMullen, and I'm on a mission to bring quality level physics and math education to everybody. And eventually, with time, I want to explore other fields as well. But for now, these lectures on YouTube, these are my first step in the direction of accomplishment of my mission. I believe that education is the path to a better life. Education opens our minds in ways that nothing else does. It helps us understand things. It helps us with developing logic. It helps us with developing problem-solving skills. And these skills are very, very important to living a good life. Alright, with that being said, let's now talk about today's class. Today's class is lecture number 8 on propagation of error. In this lecture, we're going to solve problems based on electrical resistance, resistivity, and heat dissipated in electrical systems. Now, you might say that, hey, we don't even know what is resistance yet, resistivity, and heat dissipated in electrical systems. So why are we solving problems based on those topics? You're right to feel so. However, you're going to see that these problems do not require details of what electrical resistance is or resistivity is or where they come from. All you will need to know are a few formulae. And I'm going to provide you those formulae to solve these problems. Alrighty, without any further delay, let's begin our lecture number 8. Let's see what the problem number 1 says. Problem number 1 says, determine the equivalent resistance of a circuit. Here we are talking about what kind of circuit? An electrical circuit, consisting of two resistances, uppercase R1, 100 plus minus 50 ohms. This symbol here, omega, it's an uppercase omega. It is called as ohm. What is it? It's an SI unit for resistance. Alright, so this circuit consists of two resistances, R1 and R2, and we're given the numerical values of these two resistances along with their uncertainty. We're to find the equivalent resistance of the circuit when these resistances are connected in series with each other, and in part B, in parallel with each other. So before we solve this problem, very quickly, let's think about what resistance means. I know I said that we do not need to dive into the details of what resistance means. However, the term resistance, the word resistance itself literally means obstruction, resistance to something. It's like opposition. So it is electrical resistance. That means it is going to provide resistance to what? To the flow of the current, because that's what happens in electrical circuits. Electrical current flows in electrical circuits. So the property of this material or the wire that offers resistance to the flow of the current, that is resistance. Okay, and we already saw that resistance is measured in ohms. Now resistance in an electrical circuit, okay, it is represented as a zigzag line. This is a resistance. Let's call this as R1. Okay, and here's our R2. The first problem, problem A, says these are connected in series. So they are connected like this, like they're holding hands in series. While connecting in parallel, what would that mean? Connecting in parallel would mean, okay, let's see. Here is our R1. Here's our R2. And let's connect them in parallel. Now there's more than one way to represent how these are connected, but this is one way. R1 and R2 are here connected in parallel. So what happens when resistances are connected in series or parallel is that they act as if these two resistances, these are replaced by a single resistance. Call it as R equivalent. S is for series. So these together, R1 and R2, when connected in series, they will act as if instead there was only one resistance, whose value is this R equivalent. What the value of R equivalent is, we're going to look at the formula for that. And similarly, when they are connected in parallel, as here, these are also going to act as if these were instead one single resistance, R equivalent, in parallel. Now when two resistances, these are connected in series, let's say R1, part A, and R2 are in series, then R equivalent in series is simply R1 plus R2. And in part B, when they're connected in parallel, R1 and R2 are connected in parallel. Now their reciprocals add up to give the equivalent resistance. So R equivalent parallel equals 1 over R1 plus 1 over R2. And by solving this, you could solve for R equivalent parallel. Now what if you had more than two resistances that are being added in parallel or in series? So let's say we had a third one, R3 here. Then you will add that in series as well. Similarly, if I had R3 over here, I'll just say 1 over R3. Similarly, now you can extend this pattern in series if you had R4. Just go ahead and put R4 here. In parallel, if you also had R4 being added, 1 over R4. You see the pattern here? So if you say that n number, n could be anything. N could be 2, n could be 5, n could be 10, n could be 0. N number of resistances or resistors are added in series. What is their equivalent resistance? R equivalent in series will be R1 plus R2 plus R3. Keep on going till you hit Rn. You can write this as Ri, summation of Ri, where I goes from 1 to n. So this is a compact form of writing this above equation. Hopefully you have seen the symbol for summation before. This is again a sigma symbol. Okay. Now, what if you had, let's call it M now, m number of resistors are added in parallel. How do you find R equivalent for this? Alright. First of all, you will write R equivalent equals, 1 over R equivalent, 1 over R1 plus 1 over R2 plus 1 over R3, so on, till you get to 1 over Rm. So once again, you can write this as summation of I going from 1 to m, and this summation is of 1 over Ri. Simple so far? Easy? Let's go ahead and now write down the values of R1 and R2, and then we're going to solve for the equivalent resistance along with the uncertainty when those resistors are added in series in part A. Then we're going to solve the same problem when those same two resistors, they're added how? In parallel. Alrighty. Let's get the numerical values of R1 and R2. Okay, so this is our R1 and R2. We could further write this as R1 bar plus minus delta R1 bar. Now we have used this kind of notation before. Watch some previous lectures and you will see that this is the average value of R1 plus minus the delta R1 bar is the mean absolute error in R1. And likewise, R2 can be written as R2 bar plus minus delta R2 bar. Alright, so from here we get that R1 bar. This R1 bar is equal to 150 ohms. And delta R1 bar, that would be equal to what? 20 ohms. Okay, moving on to R2 bar. Here R2 bar equals 100 ohms. And delta R2 bar is equal to 15 ohms. What are we solving for? We're solving for R equivalent in series. That will be equal to R1 plus R2. But R1 is not just one number. It is R1 bar plus minus delta R1 bar. And we have seen before that when we add or subtract numbers, what happens to the errors or the uncertainties? They simply add up. So this problem, part A, is quite straightforward. This is going to be simply R1 bar plus R2 bar. And then we're going to have here what? Plus minus delta R1 bar plus delta R2 bar. Okay, what is the value of R1 bar? 150 ohms. It's right here. Plus R2 bar, 100. Plus minus delta R1 bar, 20. Plus delta R2 bar, 15. Now I'm going to put parentheses around this entire expression and put ohms on the outside. Okay, what does this give us? What does it give us? 150 plus 100 is 250 plus minus 35 ohms. Now this was fairly straightforward. Part B though is not so straightforward. Let's see how to do part B. Now for part B, common sense says here that R equivalent parallel equals 1 over R1 plus 1 over R2. And if you solve this for R equivalent, so this gives us R1 times R2 divided by R1 plus R2. We can write R1 plus R2 at the bottom as R equivalent in series. And at the top we have same thing, R1 times R2. So now we have R1, R2 and R equivalent S series that are being multiplied or divided to each other. So we should use the formula for propagation of error when the physical quantities are multiplied or divided. But when we do so, it gives us wrong answer. It doesn't work for this case over here. The formula for propagation of error for multiplication and division. Why it doesn't work? Let's not get into that. That's going to be a very involved discussion. It's beyond the scope of this lecture. So I'm not going to get into this. But I do want you to know that this will not work. So I want you to know that if you use this formula and wrote down the percentage error or just the relative error, so relative error in R equivalent P equals relative error in R1 plus relative error in R2 plus relative error in R equivalent series, you will end up with the wrong answer. So how do we solve this problem? Let's see. Instead, here's what we're going to do. We're going to write this as Rp to the power minus 1. It is implied that this is R equivalent parallel. R1 to the power minus 1 plus R2 to the power minus 1. Now we're going to differentiate it. And when we differentiate it, what do we get? This minus sign comes out. You get minus 2 at the top, dRp. Then on the other side, on the right hand side, you get minus R1 to the power minus 2 dR1 minus, which is which minus sign? This one here is coming from there. R2, okay, let me show you how we get this minus 2. This minus 1, minus 1. This is the formula for differentiation, dR2. So from here, you can see that minuses cancel out because there's a minus sign in front of every term of this equation. Every single term in this equation is a negative term. So you could say that you can divide this entire equation by minus 1, or you could multiply it by minus 1. And when you do so, the minuses all cancel out. What are you left with? You're left with dRp and this Rp to the power minus 2. Let's bring it downstairs. What does it become? Rp to the power 2 equals dR1 divided by R1 to the power 2 plus dR2 divided by R to the power 2. And now from here, I'm going to change all the differential operators to deltas. What does that give me? Delta Rp divided by Rp squared equals delta R1 divided by R1 squared plus delta R2 divided by R2 squared. Now we are interested in solving for this delta Rp. Why? Because what do we want eventually in part B? We want R equivalent in parallel. What is that going to be? Rp bar plus minus delta Rp bar. That's what we have been doing. This Rp bar, that is going to be this one over here. While delta Rp bar, that is equal to this delta Rp. So from here we see that delta Rp equals delta R1 divided by R1 squared plus delta R2 divided by R2 squared times Rp squared. Now something is worth noticing over here, and that is the units. Delta Rp, it should have the same units as the Rp itself. And Rp should have same units as the resistance. It is ohms. Delta R1 also has units of ohms. Delta R2 does have units of ohms. And R1 squared has units of ohm squared. And R2 squared has units of ohm squared. Rp squared has units of ohm squared. So when you multiply them out, you can see that ohm squared in the first term cancels out this ohm squared outside the parentheses. Why? Because when you bring this Rp inside the parentheses, when you open these parentheses, Rp squared will multiply the first term plus it multiplies the second term. So you see that ohm squared cancels out, and you are left with the units of ohms on the right hand side as it is on the left hand side. So dimensionally this equation is correct. Let's now plug in the numbers here. And Before we plug in the numbers in this equation to solve for delta RP, let's go ahead and solve for RP first. We know that RP is equal to R1, R2 divided by R1 plus R2. And I'm not writing it here, but all these bars here are implied. So R1 was 150 here. R2 is 100. Okay. So R1 is 150. R2 is 100. Ohms times ohms divided by 150 ohms plus 100 ohms. What does this give us? 150,000 ohms squared divided by 250 ohms. Very quickly, I'm going to cancel out one of the ohms at the bottom with one of the ohms at the top. This 0 cancels out one of the zeros at the top. And now 25 times 6 is 150. So 25 times 60 should be 1500. So the answer for RP bar is 60 ohms. So when you add the resistance in parallel, the equivalent resistance decreases. When we added them in series, the equivalent resistance was 250. When we look at the chapter on resistance, we are going to understand why the resistance decreases when added in parallel and why it increases when added in series. Now is not the time to do that. Now is the time to solve for this delta RP bar. Let's go ahead and do that. So we're saying that delta RP bar equals R1 bar, delta here, alright, divided by R1 bar squared plus delta R2 divided by R2 bar squared times RP equivalent, and that's going to be squared as well. And we know the RP's value is 60. Okay, delta R1 bar. It was 20 and delta R2 bar was 15. Alright, let's go ahead and plug those values in before I forget them. Yep, I can easily forget pretty much anything. R1 bar squared is 150 and R2 bar squared is 100 squared. And of course there are ohms here, but you know that at the end we're going to left with just 1 ohm at the outside, which I have already shown you. So I'm not going to write ohm with every single number now. You can, but all it's going to do is make it look more, untidy and cumbersome. Let's not do that. Alright, now when we solve this, what do we get? I'm going to write this down. 20 divided by 150 times 150 times 60 times 60 plus 15 times 60 times 60 divided by 100 times 100 ohms. Alrighty, zeros. And then, alright, we're going to then do 2 times 3 is 6. So 3 goes into 3 goes into 6 2 times. 3 goes into 15 5 times. Same thing over here. 3 goes into 6 2 times. 3 goes into 15 5 times. 5 goes into 20 4 times. So what do we have in the first term? 4 times 2 times 2 is 16. 16 divided by 5. Let's look at the second term now. 0, 0, 0, 0. So 6 times 6, 36 times 15. What is 36 times 15? Let's see. 36 times 15 is 540. 540 divided by 100 ohms. Here, zeros canceled out again, and this gives us 5.4 here. So let's go ahead and write down 5.4. What is 16 divided by 5? That will be 3.2. Yep. So we get here 3.2 plus 5.4 ohms. This gives us 8.6 ohms. So our R equivalent parallel, the answer for part B, is going to be 60 plus minus 8.6 ohms. Now, are we done? Yes and no. The rules for uncertainty say that the uncertainty must be up to the same number of decimal places as this number, which is a whole number, 60. So that means this 8.6 must round off to a whole number. What is the nearest whole number? 9. So our answer is 60 plus minus 9 ohms. That's your R equivalent P. Problem number 2. Perhaps a lot of new terms. For example, voltage. Maybe not so much though. Voltage, volts. If you have ever used batteries, I'm sure you have seen some batteries are 1.5 volts, some are 6 volts, and so on. So voltage is perhaps not such a new term for us, and nor is current. I mean, sure, maybe you do not know that the symbol for current is I, but suddenly you have heard of electric current before. Resistor, we just learned about resistor. So this particular problem, it is based on something called as Ohm's law. What is Ohm's law? Ohm's law says, for example, you take a battery. Here's your battery. Let's box it in. You connect this battery. You connect this battery to a device, such as a bulb. And let's say this is the switch over here. Okay. This is the switch. Now, when you close the switch, what will happen is that current will flow out of this battery into the bulb, and the bulb is going to light up, right? So what we do in terms of electrical circuits, the battery is represented by two lines. One line is shorter and the other line is longer. All right. Not a tilted line. We want a straight line. Now this is not exactly straight. Let's see if I'm capable of drawing a vertically straight line using a drawing tool. And seems like I can. Next thing what I'm going to do is I'm going to connect wires now to this battery. Let's use blue color for the wire. And again, I'm going to use the shapes tool to draw a straight line. Next thing I'm going to do is I'm going to draw this resistor here now. The bulb is represented by a resistor. And the resistor is a zigzag line. So here, the bulb is represented by the resistor R. The battery is represented by two vertical lines where one line is longer than the other line. Why is one line longer than the other line? I'm sure that you have noticed that in the battery, there's a positive terminal and there's a negative terminal. The longer line is the positive terminal and the shorter line is the negative terminal. So here is your battery with voltage V. Okay. And once we connect the switch, once this circuit is completed like it is shown, then the current is going to flow, and the current is represented by letter I. So current is going to flow from the positive to the negative terminal like this. This is the conventional electric current. You may think that I've heard the current is flow of electrons, and electrons are negatively charged. So if current is the flow of electrons, then it should flow in the backward direction. But conventionally, we say that the current is flowing from positive to the negative terminal of the battery. Now the Ohm's law says that the current I, here's I, that's flowing through the battery, it is directly proportional to the voltage applied, okay? And it is inversely proportional to the resistance of the battery. So when you put those things together, you get I equals V over R, which is often written as V equals IR. And this is your Ohm's law. Ohm's law says that voltage equals electric current times resistance R. In this case now, the resistance, we are asked to find the percentage error in the resistance R. Okay, so from the same equation, R equals V over I. What are we given? We're given the value of V to be 50.0 plus minus 0.5 volts. Let's write it down. 50.0 plus minus 0.5 volts. And we're also given the value of I. What is that equal to? That is equal to 200 plus minus 1 milliampere. So uppercase A is for ampere. Ampere is the SI unit for current. So I already forgot. 200 plus minus 1. Alright. 200 plus minus 1 milliampere. So A is A-M-P-E-R-E, ampere. You might hear some people say amperage, that the amperage of this device is whatever, 200 plus minus 1 milliamperes. They are referring to the current flowing in the device. Alright, so we know that R equals V over I. We are asked to find the percent error in the resistance R. What is percent error in anything? Percent error or percentage error in R. Okay, so we know that R equals what? R is equal to V over I. And when you have some quantities that are being multiplied or divided, how do you find the percentage error? The percentage error on the left hand side, which is delta R over R times 100, will be equal to percentage error in the voltage divided by the, just the percentage error in the voltage. I was saying delta V divided by V times 100. Plus percentage error in the current. Okay. Now delta V is given to be 0.5 volts and V is given to be 50.0 volts. Let's write it down. 0.5 volts divided by 50.0 volts times 100 plus delta I. Delta I is 1 and I is 200. Okay. So this is 1 divided by 200, milliampere at the top, milliampere at the bottom, times 100. Volts cancels out in the first term. Milliampere cancels out in the second term. Now by now I have shown it to you several times in the previous lecture that 0.5 divided by 50.0, you divide by what? 10 to get rid of the decimal. And when you do so, what do you get? You get 5 divided by 500 times 100, which is this 100 over here, plus 100 divided by 200. Okay, that gives us 1 plus 1 half, which is equal to 3 halves or 1.5% error. Okay, so this was the percentage error in R. What if we were asked to solve for, solve for delta R? How would you get that? Now we have just solved for delta R over R times 100 equals what? This equals 1.5. So from here, if you are to solve for this delta R, what will that be equal to? Delta R will be equal to 1.5 divided by 100 times R. And what is R equal to? R is equal to V divided by I. Okay. What is V equal to? V is equal to 50 volts and I is equal to 200 milliampere. Okay. So 50 volts and over here it was 200. Alright. It was 50.0. 200 milliampere. Now, we should take care of the units here. Milli is here 1.5 times 50.0 divided by 100 times 200 volt over ampere. And this milli over here, in place of milli, I can write 10 to the power minus 3 at the bottom. Okay. All right. What do I get now? Now I'm going to solve this. So I have 1.5 at the top, which I can write as 15 divided by 10 times 50. If you want to write that as 500, that is get rid of the decimal, then you should divide it by 10. 50 divided by 10 is 50.0. 100. And this 100 is this one over here times. Okay, that's a hideous multiplication sign. 1 over 200, where the 200 is this 200 over here, times 1000. And where's that 1000 coming from? This 10 to the power minus 3, it goes upstairs, gives you 1000. What do we have now? Okay, let's see. This 100 and this 10. These 3 zeros cancel out, 3 zeros of the 1000. 200 has 2 zeros. Let's go ahead and cancel out these 2 zeros with 2 zeros of the 500. What do we have next? We have this 2 at the bottom and 10 gives us 20 at the bottom. At the top I have 15 times 5 is 75. What do we get? We get 7.5 divided by 2 ohms, which is same as 3.75 ohms. This is your delta R. So your answer would be, if you were to answer it in this form, that would be V over I, which is equal to R plus minus delta R. And V is equal to what? V is equal to 50.0 volts divided by 200 milliampere plus minus delta R. We just got delta R to be 3.75. So let's go ahead and put in 3.75 ohms over here. And 50 divided by 200 times 10 to the power 3. 10 to the power 3 is coming from this milli. Milli is 10 to the power negative 3. 10 to the power negative 3 goes upstairs, becomes 10 to the power 3. Divided by 200 and volts divided by amperes gives you ohms. Plus 3 plus minus 3.75 ohms. What do we get here now? 50. Okay, so that is 50 times 1000 divided by 200 plus minus 3.75 ohms. 2 zeros cancel out. 2 goes into 10 5 times. 5 times 50 is 250 plus minus 3.75 ohms. Okay, now here we need to apply the rule of significant figures for uncertainty. Since the actual number 250 is a whole number, therefore this uncertainty must also be a whole number. So your answer will be 250 plus minus 4 ohms. This is your full and final answer. Alright, so these two problems, number 1 and number 2, both are based on resistance, but they're different problems. The first problem is based on adding the resistance in series and parallel and finding the equivalent resistance and the uncertainty in the resistance. And the second problem is based on Ohm's law. Let's see what the third problem is based on. Problem number 3. The resistance uppercase R, the radius lowercase r, and the length lowercase l of a metal wire are measured to be 50 plus minus 5 ohms. So this is your resistance. The radius lowercase r of the metal wire is 10.00 plus minus 0.1 millimeters. And the length L of the wire is 20.0 plus minus 0.2 centimeters, respectively. What is the error or uncertainty in the calculation of resistivity of the above mentioned wire? So a couple of new things over here. First thing is we're dealing with a metal wire, and here's your metal wire. Metal wire is of the shape of a cylinder. Okay. And this is the length L, which is given to be 20.0 plus minus 0.2 centimeters. And here's the radius R of the metal wire. And the radius is what? 10.0 plus minus 0.01 millimeters. Did I say 10.0? It is 10.00. Okay. I heard myself speaking it wrong. Reading 10.00 and saying 10.0. Happens sometimes. I mean, when you're trying to teach, your mind has to coordinate between different tasks. You have to be thinking about what you're doing, what's coming up next, what you're writing, what you're reading, and what you're speaking. So you need to synchronize all those things, and once in a while, they get out of sync. What just happened? 10.0 over here. Anyway, okay. Now we are to find the error or the uncertainty in the calculation of resistivity. Resistivity. What is resistivity? The resistance of a wire. It is directly proportional to the length. The further the current has to travel, the more obstruction, the more hindrance it's going to experience along its way. And this resistance is inversely proportional to the area. If you increase the area of this wire, which is the cross-sectional area, then the current is going to get more pathways to travel along this path, to travel along this wire. You can think of this as yourself traveling on a road. The longer is the length of the road, the longer you have to travel along the road, the more is the number of people you're going to encounter. And each person that you're encountering on your way is offering resistance, is providing resistance. But if you widen the road, that is, you increase the area, and then you will have more pathways to travel along the road. So I hope that this makes sense. Why the resistance? It is directly proportional to the length of the wire and inversely proportional to the cross-sectional area of the wire. Okay, now when you take away the symbol of proportionality, you introduce a constant of proportionality, which is called as resistivity. So what happens is R equals rho times L over A, where this rho, it is the resistivity. Now resistivity, it's an interesting parameter. The resistance of a wire, it changes in accordance with the length of the wire and the cross-sectional area. The longer the wire, the more is the resistance. The more the cross-sectional area of the wire, the lower is the resistance. Resistance also depends on the temperature of the wire. Okay. Now there is something that is fixed for a given material, rho. The resistivity, it is a characteristic of the material. It depends on the material only and the temperature. So if you have gold, it will have its specific value of resistivity regardless of the cross-sectional area and regardless of the length of the wire. Silver will have a different resistivity, copper will have different resistivity. So every material has its own resistivity, which depends only on the material and on the temperature. Okay. So when you're giving the characteristics, the properties of a material, one of the electrical properties that is mentioned is the resistivity. In this problem, we are to find the error in the calculation of resistivity of the above mentioned wire. So from this equation, rho equals RA over L. And we already said that what kind of wire is it? It's a cylindrical wire. So its area of cross-section will be pi r squared over L. Now we have this formula for the resistivity. Let's write down what else are we given. We're given the value of the resistance, okay. R is given to be 50 plus minus 5 ohms. The radius is given to be 10.00 plus minus 0.01 millimeters, and the length is given to be what? 20 plus minus 0.2, okay, 20.0 plus minus 0.2 centimeters. These are all the numerical values given to us. Using these, we want to find out the delta rho, which is the uncertainty in the rho. Okay. All right. And from there, we could definitely measure the percentage uncertainty or the percentage error or the percentage accuracy in the resistivity. Let's see how we'll do it. We know that rho equals what? Rho is equal to R pi r squared over L. Okay. So from this equation over here, using the rules of propagation of error, we're going to write delta rho over rho equals delta r over r. Now this pi over here, it's a constant. What is the uncertainty in a constant? 0. So we don't need to bother with this. Moving on to this r squared next. The power 2 comes out as what? It comes out as the coefficient times delta lowercase r over r plus delta L over L. Okay. Now to solve for delta rho, we also need to solve for rho. So from here, you could multiply the entire equation by rho, and that would solve for delta rho on the left hand side. That will give you delta rho equals what? Delta r over r, both uppercase, plus 2 delta lowercase r over lowercase r plus delta L over L times rho. And what is rho equal to? R times pi, okay, move it up, times lower r squared divided by L. Okay, now we're going to plug in the values. R is 50 plus minus 5. Okay, let's go down and write down these numbers. 5 over 50, both ohms, plus 2 times delta R. Delta R was what? 0.01 millimeters divided by 10.00 millimeters plus delta L over L. What's the value of delta L over L? over here, 20.0 plus minus 0.2 centimeters. Okay, that is 0.2 divided by 20.0 centimeters at the top, centimeters at the bottom, times. Now, when we plug in the values here for the resistivity, we need to make sure to convert them all into SI units. Okay. All right. So R, uppercase R. What is uppercase R over here? 50 ohms. Let's go ahead and write that down, 50 ohms. Then I have pi. Let's leave that as pi. Then I have radius squared, which is 10.00 millimeter. I'm going to change this to what? I'm going to change this to meters. So that becomes 10.00 millimeters will become 0.010 meters. Let's write it that way. 0.010 squared. And then there will be this meter squared divided by L. L's value is 20.0 centimeters, which in terms of meters would be what? 0.2. Okay. So very clearly we see over here that one of the meters at the bottom cancels out one of the meters at the top for the resistivity. And when we come inside the parentheses for the relative errors, all of the units cancel out. 1 over 10 plus. This will give us 2 divided by, okay, green colored, 2 divided by 1000 plus. Third term, what does this give us? 2 divided by 200. Times. Alright, let's go ahead and calculate the resistivity. What do we have? We have 50 times pi. Where's pi? I got it. Times what? 0.010 squared divided by 0.2. 0.0785. Okay. 0.0785 ohms meter. Okay. Ohms meter is the unit for the resistivity. I see it's cutting off. Let's move it like this. Alright. Now over here, inside the parentheses, 1 over 10 is 0.1. 2 divided by 1000 is 0.002. 2 over 200 is 0.01 times 0.0785 ohms meter. What does this give us? We will have 0.112 times 0.0785 ohms meter. Multiply them out and you will get delta rho. Okay, times 0.112. Boy, 0.00879. If we are to keep all the 3 sig figs here for the resistivity, then for the uncertainty, we should have 4 decimal places because this resistivity is up to 4 decimal places. So that means it truncates over here 0.0088 ohms meter is your delta rho. Okay. Now, if we were to find the percentage error in the resistivity, then what would we do? Then we have this equation like from here. we know that the second term here, or the second factor, is just rho. So what we have is delta rho equals 0.112 from here times rho, whose numerical value is 0.0785 ohms meter. Now I could rearrange this equation. I could say delta rho over rho equals 0.112. So what does this give us? This gives us the relative error in rho. Okay. While this over here, delta rho, this was simply error or uncertainty in rho, where rho is the resistivity. Now how do you figure out the percentage error or the percentage uncertainty or the percentage accuracy in rho, the resistivity? Simply by multiplying this by 100. That gives you what? Delta rho over rho times 100 equals 11.2%. So here we have found three things here in this problem. This problem was certainly different from what you've been doing. It was based on resistivity, a totally new concept for you probably. But hopefully you got enough insight into understanding what resistivity is, what resistance is, what is the formula, and how does the formula make sense conceptually speaking. Alright, let's move on to problem number 4 next. Problem number 4. It says that the maximum error in the measurement of voltage, current, and the time for which current flows in a circuit are 3% each. What is the maximum percentage error in the measurement of the heat dissipated in this circuit during the time the current is flowing in the circuit? Now, you can see that this is a multiple choice question. We have 4 answer choices. Now, in a general multiple choice question, especially a qualitative one, you may have more than one correct answer, right? I'm sure you have seen that. However, in this problem, there will be only one correct answer. Why? Because this problem is asking us to solve for maximum percentage error in the heat dissipated. So we are asked to solve for the numerical value of the percentage error in the heat dissipated. There's going to be only one answer for this. Does it make sense? I hope it does. All right, let's see what's given to us. We are given that the maximum error in the measurement of voltage, current, and time, all 3 of them, is 3%. So let's go ahead and write them all down in just one equation. How? Let's see. Delta V over V times 100. Delta V over V times 100. This is percentage error in voltage. It is same as the percentage error in the current, which is delta I over I times 100. And that in turn is same as percentage error in the time, which is delta T over T times 100. All 3 of them are equal to what? 3%. All right. What are we asked to solve for? We're asked to solve for the maximum percentage error in the measurement of the heat dissipated. So let's talk about heat for a second here. What is heat? What kind of physical quantity it is? What kind of parameter it is? It is energy. I'm sure you already knew this. Heat is a kind of energy. Just like there's kinetic energy, there's potential energy, there's nuclear energy, there's another kind of energy called as the heat energy. Now, what is energy? Energy is defined as what? It is the ability to do work. So energy has the same dimensions as does the work. So heat energy is going to have the same dimensions as that of work. Keep this in mind, okay? Next thing we're going to look at is, it might look like, hey, why are we talking about power? Because that's what we're about to talk about. Power. Power is defined as work per unit time. You will see very soon why we're talking about power. Okay, now instead of work, I'm going to substitute heat energy here because they are dimensionally same things. Heat energy divided by time. So that gives me P for power equals H for heat, T for time. Now in case of electrical circuits, power is defined as voltage times current. So voltage times current, that equals H, the heat divided by time. Upon rearranging this equation, you can see that H equals VIT. Using this equation, we can very easily figure out what is the percentage error in the heat energy dissipated. Okay, so delta H over H times 100 equals what? The percentage error in the voltage, which is delta V over V times 100 plus what? Percentage error in the current I. Okay, that is delta I over I times 100 plus percentage error in the time, delta T over T times 100. Okay, here we go. Now we know that the percentage error in voltage and the percentage error in the current and the percentage error in the time for which the current is flowing through the circuit, all three of them are equal to what? 3% here. So let's go ahead and plug in each of the three terms in this equation as 3. So 3 plus 3 plus 3. What does this give us? 9%. So there's 9% error in the measurement of the heat dissipated in the circuit for the time during which the current is flowing in the circuit. So look at this. It is such a simple problem. It is a mini problem. I mean, that's what you should call it, a mini problem. There's not much to do here as long as you know the formula for power, you know the relationship between the power, work, and time, and you do know that heat and work, they're about the same things. As long as you know those things, there was really not much to do in this problem. This was not a very challenging problem. Not every problem will be challenging, but it is important to do these kinds of problems. Why? Because it builds up your confidence. So when you do simple problems, you see that you can do all these kinds of problems. It makes you feel good about yourself. And then you can move on to harder problems, because until you do harder problems, you're not going to get too far, are you? All right, with that being said, let's move to problem number 5 now. Problem number 5. The maximum accuracy in the measurement of resistance, current, and time for which the current flows in an electric circuit are 3%, 2%, and 1% respectively. The maximum accuracy in the calculation of the dissipated heat is 4A%. The value of A is equal to what? All right, so let's first make a list of what is given to us. Then we're going to write down what we want to solve for, what we are given, what we have, what we want. How do we go from what we have to what we want? How to connect these two? That's the main goal of every problem. The maximum accuracy in the measurement of resistance is 3%. So let's go ahead and write that down. Delta R over R times 100 is 3%. The maximum accuracy in the measurement of current is 2%. Okay, so that would be delta I over I times 100 is 2%. Last, the maximum uncertainty or accuracy in time is 1%. Okay, delta lowercase t over t times 100 is 1%. Then we are told that the maximum accuracy in the calculation of the dissipated heat is 4%. So, and that is delta H over H times 100 is equal to 4%. Solve for A. That's your problem. Now, just in the previous problem, we saw that H was equal to VIT. However, in this problem, we do not have V. So you see that we have R, which is not in the equation for H. We have I, that is in the equation for H, so that is good. T is in the equation. The left-hand side is equal to 4A. But this V over here, we're not given any information about it. But are we really not given any information about it? We are. How? In the second problem, we looked at something called as Ohm's law. Remember it? What did it say? V equals IR. So, if I replace this V equal to IR, then H will be in terms of I, R, and T only. And we are given the percentage errors in those three quantities. And from there, we can solve for the percentage error in heat dissipated. And from there, we could solve for A. Let's see how we do it. So what I'm saying is, in place of this V, put in IR. See this? From here, we get I squared, this I times R times T. So delta H over H times 100 will be equal to the percentage error in this I squared, which will be this 2. It becomes the coefficient. How? Like this. 2 times delta I over I times 100 plus the percentage error in the resistance R. That is going to give us delta R over R times 100 plus the percentage error in the time t. That gives us delta T over T times 100. Now we're given these numerical values. The numerical value of the percentage error in resistance is 3%. Okay, so that is over here. This one over here, 3%. Then we have, what else? We have the percentage error in the current, 2%. All right, let's write that down. 2, which is this 2, times 2%, and this 2% over here is the delta I over I times 100, which is given to us, plus. Then we have this percentage error in the time. What is that equal to? 1%. All right, let's write that down. 1%. And on the left hand side, I have 4%. So let's go ahead and not write the percentage sign in any of the terms. I get 4A on the left hand side is equal to 8 on the right hand side. Divide both sides by 4 and that gives you A equal to 2. And this is what we are asked to solve for. A. Okay, no, this box is just not going to do it. Here we go. Much better. Okay, so this was our problem. I think this was a very, very straightforward, very easy problem. Hopefully you all got it. If not, you have a benefit. It's a recorded video. Rewind it. If you still have questions, drop those questions in the comment section. Problem number 6. It says the percentage error in the measurement of the length and diameter of a silver wire is 3%. Compute the percentage error in the calculation of the resistance for that wire. Okay, so resistance needs to relate to what? Length and diameter. Now, in one of the previous problems, we said that a wire is of the shape of a cylinder. Okay? And then we also talked about the resistivity and the resistance and their relationship to the cross-sectional area of the wire and the length of the wire. So let's see if we can somehow relate all those things to calculate for the percentage error in the calculation of the resistance. So here we are given that delta L over L times 100 is equal to what? 3. Delta D over D, here D is the diameter, is also equal to 3. Solve for or calculate delta R over R times 100. Okay. Now we know that R is equal to rho times L over A. Okay. So if you want to calculate the percentage error in the resistance, then we are going to use the rules of propagation of error as applied to this formula. Given temperature, the resistivity is a constant. We are going to assume that its value is exactly known at a given temperature. When its value is exactly known, this implies delta rho is equal to 0. And when we apply the rule of propagation of error to this formula over here, which formula? This formula, R equals rho times L over A. Then we are going to use that delta rho is equal to 0. Okay, but before we do that, let's write this equation as rho L divided by cross-sectional area A of the wire is pi times R squared. We're not given the percentage error in R, the radius, but we are given the percentage error in the diameter. So let's go ahead and write R, the radius, in terms of the diameter D. R is equal to D half. So this gives us rho L, denominator of the denominator, which in this case is 4. How? Over here. This 2 over here, its square gives you 4. So that becomes the numerator. So that comes up here, times pi d squared. Now when we write down the percentage error in R, you're going to see that this 4 over pi, these are constants, and constants do not have any uncertainty associated with them. There's absolutely zero error associated with this 4 over pi. So when we write down the formula delta R over R times 100, we're going to disregard this 4 over pi. Pretend like this doesn't even exist. Alrighty. So this is equal to delta rho over rho times 100 plus, we have, what do we have? This L over here. Delta L over L times 100 plus the last one. We have this 2 comes down as the coefficient 2 times delta D over D times 100. Now what did we say about this delta rho? This is equal to 0. Why? Because this is a silver wire and its resistivity is exactly known at the given temperature. Therefore, the uncertainty in the resistivity is 0. Delta L over L times 100 is 3, and also the percentage error in the diameter is 3. So that gives us This one is 3 plus, okay, plus 2 times delta D over D times 100 is also 3. So the answer is 9%. So that's all we were asked to solve for. I mean, this has got to be the easiest problem, right? It couldn't be any easier, could it be? But if you still have any questions, drop me in the comment section. And I'll try my best to address all your concerns and your questions regarding the chapter that we are working on. Let's move on to the last problem of this lecture. Problem number 7, the last problem of this problem set. It says that the resistance R, the length L, and the diameter D of a wire are measured as 55 plus minus 5 ohms, that is the resistance. The length is 22.00 plus minus 0.02 centimeters, and the diameter is 1.1 plus minus 0.1 centimeters. What are we asked to solve for? We're asked to solve for find the value of the resistivity of the material of the wire and the corresponding percentage error in the calculation of the resistivity. Okay, very well. Let's write down what is given to us. We're given the value of the resistance R. It is equal to 55 plus minus 5 ohms. So this is basically R bar plus minus delta R bar. By simple comparison, you can see that R bar should be equal to 55 ohms and delta R bar should be equal to 5 ohms. You see this? Okay, I'm sure you do. So from here, R bar equals 55 ohms and delta R bar equals 5 ohms. I'm not going to write this down for every single quantity, but I wanted to show this to you for at least one. Next thing is the length of the wire, L. It is equal to 22.00 plus minus 0.02 centimeters. And the last is the diameter. What is the diameter equal to? The diameter is 1.1 plus minus 0.1 centimeters. Okay, we're asked to solve for two things in this problem. The first is the resistivity of the material, and the second is the percentage error. We're going to do a third thing as well. We're going to also go ahead and calculate the error in the resistivity. And we are going to find out the relative error in the resistivity. Relative error is delta rho over rho. Delta rho alone is the error or the uncertainty. Okay. Now to solve this problem, the equation that I always begin with is the equation for resistance, R. R equals rho times L over A. Let me write an uppercase L here because that's what I wrote up here. So this L is the length of the wire and A is the cross-sectional area of the wire. From this equation, we can solve for rho. That would become R times A divided by L. Since A is the cross-sectional area, we write this equal to pi R, lowercase r is the radius over L. Now, we're not given the value of the radius, we're given the value of the diameter. So what I'm going to do is I'm going to write down this radius in terms of the diameter. We know that radius r equals d over 2. So if I square radius, I have to square d over 2, which gives me d squared divided by 4. So in place of r squared, we're going to substitute d squared over 4. Let's go ahead and do that. R times pi d squared over 4L. Now we're asked to solve for rho. To solve for rho, you have to plug in the value of R D and L in this equation. Let's go ahead and do that. Rho equals, R is the resistance, 55 ohms from over here. Then I have pi right over here. Then we have what? D squared. What is D equal to? 1.1 centimeter. So I'm going to write 1.1 squared centimeter squared divided by 4, which is this over here, times L. What is L equal to? L is equal to 22.00 centimeters. Okay, so here's our L, 22.00 centimeters. Now right away you will notice that centimeter cancels out one of the centimeters at the top. What are we going to get when we multiply these numbers out? Let's see. This gives us 2.375829444. But I'm going to stop here. What would be the units? This ohm times a centimeter. Okay, ohms, centimeter. So we're done with the first part of the problem where we were asked to solve for what? The resistivity of the material. Next, we're going to calculate the percentage error in the calculation of the resistivity. All right. So to figure out the percentage error in what? In rho. Let's write down the equation for rho. What is the equation for rho? That is this equation over here. R pi d squared over 4L. R pi d squared over 4L. Now in this equation over here, this pi and 4, these are constants. What is the variation? What is the error in the constant? 0. So this implies the error in 4 and pi is what? 0. So when you're writing down the percentage error formula for rho, disregard pi and 4 on the right hand side. And when you do so, what do you get? You get delta rho over rho times 100 equals. On the right hand side, you will have delta R over R times 100 plus. Now here, this 2, this comes down as the coefficient 2 times the percentage error in the diameter D. That is delta D over D times 100. And last, this L over here, the percentage error in the L. What is that equal to? That is equal to delta L over L times 100. What are the values, the numerical values of the percentage error in resistance, diameter, and length? We don't know. We're going to have to calculate. So for percentage error in the resistance, this is your delta R, this is your R. So it is 5 divided by 55. 5 ohms for delta R and 55 ohms for R times 100 plus 2 times delta D over D. Delta D, 0.1 centimeters. D, 1.1 centimeters. All right. So 0.1 centimeters divided by 1.1 centimeter times what? 100 plus delta L over L. Here we go. Delta L 0.02, L 22.00. Okay. So 0.02 divided by 22.00, both in centimeters times 100. Okay. Now you see that how beautifully all of these units, they cancel out. Not just that, in the first term, 5 divided by 55 is equal to 1 over 11. So that gives you, I'll show you here. 5 goes into 55 11 times. We are left with 100 divided by 11 plus we have 2 times. Now go ahead and get rid of this decimal by multiplying divided by 10. That gives us 1 divided by 11 times 100. The last equation, again multiply divide by 100 to get rid of this decimal here. That will give you 2 divided by 2200, which is equal to 1 divided by 1100 times 100. What do we get? So what we get is 100 divided by 11 plus 200 divided by 11 plus 1 divided by 11. Okay. So 11 in the denominator is common in all of them. This gives us 301 divided by 11. What is this equal to? 27.36. 27.3636%. This is our percentage error in rho. Okay. Now we also said we're going to find out delta rho. But before we do that, let's return to this equation over here. We got the answer for rho to be 2.3758 ohm centimeters. But we didn't quite follow the rules of significant figures, which say that while multiplying and or dividing, the number of sig figs in the final answer must be same as the least number of sig figs in the numbers that are being multiplied or divided. For this, we are going to disregard pi and 4. Look at all the other numbers. 55, 2 sig figs. 1.1, 2 sig figs. 22.00. How many sig figs does it have? It has 4 sig figs. So the least number of sig figs are in 55 and 1.1, 2 in each. So the final answer must round off to how many sig figs? 2 sig figs. So the final answer for rho should be 2.4 ohms centimeters. Okay, so now we have percentage error in rho and rho. Let's go ahead and calculate delta rho. How do we do that? Problem didn't ask us to solve for delta rho explicitly, but we are going to go a step further and do it anyway. So delta rho over rho times 100 equals what? We just solved for it. 27.3636. Let's rearrange this equation to solve for delta rho on the left hand side. You get 27.3636 rho over 100. And the value of rho, I'm going to use this long value of rho here. This is another thing we had learned when we were doing calculations with sig figs. Keep all the digits or the most number of digits that you can for as long as you can. Get the final answer and then round it off to the appropriate number of the significant figures. So for rho, we're going to use 2.3758. 2.3758. I'm just writing it here so I don't have to scroll back up to check the answer for rho. So I get 27.3636 times 2.3758 divided by 100. What do you think we're going to get? Let's see. That gives us 65.0104 divided by 100. That gives us 0.65 ohms centimeter. Why? Because this 27.36, it doesn't have any units, nor does this 100. However, this rho has units of ohm centimeters. And besides, we have been discussing that the uncertainty or the error would have the same units as the quantity for which it is defined. All right, now let's write down the rho, the resistivity in its proper form, which is going to be rho plus minus delta rho. And we said that rho should be 2.4. How many suffix does it have? 2. Plus minus 0.65 ohm centimeters. But from the rules of uncertainty, we know that the uncertainty must have the same number of decimal places as the number for which it is defined. That means this answer is going to be 2.4 plus minus 0.65. Round it up. Why? Because this is a 5 over here. It becomes 0.7 ohms centimeter. So this is rho plus minus delta rho. Alright, so this was your problem number 7. Again, not a terribly long problem, nor very complicated. Hopefully these 7 problems, they have given you a good sense of how to solve problems based on the application of propagation of error to electrical circuits, to problems of resistance, resistivity, and heat dissipated in electrical circuits. That was all for this lecture. Hopefully you had fun, you understand it, you enjoyed it. Keep studying, keep learning, keep growing. I'll see you again very soon in the next lecture, lecture number 9, where we're going to solve more problems based on propagation of error. All right, until then, have a good one.